Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Today we'll be doing aldehydes, ketones, and carboxylic acids. So, compounds containing carbon double bond oxygen as the functional group. They can be categorized in aldehydes or ketones. Of the two valencies, if one is occupied with hydrogen, then the compound is called aldehyde, and if both are occupied by alkyl groups, then the compound is a ketone. So aldehydes and ketones, they are carbonyl compounds. There are some other compounds also which contain carbon double bond oxygen. So let's study about them. So aldehyde will contain our CHO group. Ketones will contain C double bond O and two alkyl groups. Carboxylic acid will contain, apart from double bond oxygen, an alkyl group and an OH group. Now, if these are carboxylic acids, COOH group, compounds containing COOH group. Now, if this is made to react further so that the group is displaced by some other group, then the compounds are called acid derivatives. For example, when we replace OH with halogen, it is called acyl halide. When we replace it with another acid part, that is two acids react, water is taken out, and anhydride will be formed. Anhydride means minus water. So two acids minus one water will form acid anhydride. When acid reacts with alcohol, then a water molecule eliminates, and this is the acid part, this is the alcoholic part, and ester is formed. And when the OH part is replaced with NH2 part, it is called acid amide. We will study about these compounds one by one. First part is aldehydes and ketones, where the functional group is carbon double bond oxygen. It is polar in nature, and if of the two valencies, if both are occupied with hydrogens or at least one is occupied, these are aldehydes. If both are occupied by alkyl groups, these are called ketones. One carbon acid is formic acid, HCOOH. The formaldehyde of one carbon will be called formaldehyde. 3 carbon will be called propionaldehyde. 4 carbon compound will be called butyraldehyde, and so on. Substituent is attached, then the carbon which is attached to the functional group, to the aldehyde group, will be called alpha. So the prefixes alpha, beta, gamma, etc. are used in common system, whereas the prefixes 1, 2, 3, etc. are used in IUPAC system. So in IUPAC system, the naming of the compounds, aldehydes are named as alkane als. The suffix al is used for aldehydic group, and the total number of carbon atoms will decide the name of the compound. If it's one carbon compound, then meth, then ane, methane. So for example, HCHO will be called methanol. A 3 carbon compound with aldehydic group will be called propanol. So this compound, while naming the compound, we select the longest continuous carbon chain containing the functional group, and then we number the compound. So it is 2-ethyl butanol. The name of this compound will be 2-ethyl butanol. Numbering starts from that end from which the functional group is closest. In aromatic aldehydes, this compound will be called benzene carbaldehyde, but to simplify, the word benzaldehyde has been accepted. This is 2-hydroxy benzaldehyde. In common system, ortho-hydroxybenzaldehyde and or salicylaldehyde is also the name given to this compound. This is called phthalaldehyde because a compound C6H4 COH at ortho positions is called phthalic acid. So correspondingly, the aldehydic compound will be called phthalaldehyde. Then we have naming of ketones. In common system, we will name the two groups attached to the ketone group in alphabetical order and then use the suffix ketone. So this is dimethyl ketone, this is ethyl methyl ketone. E comes first. In IUPAC system, we just take the whole carbon chain and name it. Suffix used is -one. So this is a 3 carbon compound. So propane to -one, propanone. And this will be pentane to -one. Numbering starts from this end. We number the compound and then we name. Then similarly, when a compound contains both aldehydic group and functional group, both are present, then in that case aldehydic group is given preference and is considered the principal functional group, and the ketonic group is considered as substituent. So prefix is used for naming ketonic group. So numbering is done 1, 2, 3, 4, 5. 3 oxo pentane null will be the name. We can also call it 3-ketopentanyl. Similarly, this compound will be called methyl phenyl ketone in common system, and we can also call it acetophenone. This is isomerism in aldehydes and ketones. So the different types of isomerism is chain isomerism, where difference occurs on the count of type of chain. For example, this is a chain containing 4 carbon atoms. Here the chain is of 3 and methyl is substituent, but overall there are 4 carbon atoms. These are chain isomers. Similarly, pentane to -one and 2-methyl pentane, 3-methyl pentane, butane to -one are both chain isomers. Position isomerism, when the difference occurs on the position of the functional group. For example, pentane 2-one and pentane 3-one are position isomers. Third type of isomerism is functional isomerism. So ketones and aldehydes are functional isomers of each other, and the phenomena is known as functional isomerism. Metamerism arises when the functional groups on either side of the ketonic group are different. For example, methyl and propyl and 2 ethyls. The molecular formula is same, but the alkyl groups are different. So these are metamers of each other. Methods of preparation of aldehydes and ketones. So we can categorize them into 3 categories. Methods of preparation involving both aldehydes and ketones. Then second method only aldehydes, and third method only ketones. So first we will do from alcohols. So first method is by oxidation. When we oxidize alcohol with acidified potassium dichromate, it gets oxidized to its respective aldehyde or ketone, and then later on it gets further oxidized to acid. But if we remove the products at aldehydic stage, then the oxidation can be stopped. So ethanol will be oxidized to ethanoic acetaldehyde, butanol butyraldehyde, and benzyl alcohol to benzaldehyde. If we want that the oxidation should not go to the acid stage, aldehyde should remain as such, we can use pyridinium chlorochromate as the oxidizing agent. It is also known as Corey's reagent. So because aldehydes undergo oxidation readily to acids, so they are distilled off as soon as they are formed to avoid further oxidation. And if we oxidize secondary alcohols, they will be oxidized into ketones. Primary alcohols to aldehydes and secondary alcohols to ketones. So pyridinium chlorochromate can also be used to get ketone from secondary alcohol. For example, OH is attached to carbon, which is attached to 2 carbon, so it's a secondary alcohol. When we carry out its oxidation with pyridinium chlorochromate and methylene chloride, this group gets oxidized to ketonic group. The double bond is left intact. We can also use chromium trioxide in aqueous acetone, and this method is called Jones oxidation. Here also the double bond is not oxidized. For example, if we use allyl alcohol, it will get oxidized to allyl aldehyde. Because chromium trioxide is toxic, so toxicity of reagents that contain chromium, we can use a new method where chromium is not used. This method is called Swern oxidation. Here we use dimethyl sulfoxide, oxalyl chloride, and trimethylamine. So, for example, on oxidizing propanol, we can oxidize into aldehyde. Similarly, butane 2-ol will get oxidized to butanone, butane 2-one. Second method is by catalytic dehydrogenation of alcohols. So when vapors of alcohol are passed over copper at 573 Kelvin, hydrogen is lost and aldehyde is formed with primary alcohol, and ketone is formed with secondary alcohol. Hydrogen is lost. Third method is from carboxylic acids. So there are two methods. First is aldehydes and ketones can be prepared by catalytic decomposition of carboxylic acids. Carboxylic acids are heated with manganese oxide as catalyst at 573 Kelvin. So COH of one acid and OH of other acid will combine to form carbonic acid, which disintegrates into carbon dioxide and water, and H and CHO will combine to form methanol. So with formic acid, aldehyde methanol is formed. With the formic acid and ethanoic acid, ethanol is formed. Aldehydes are formed if one of the acid is methanoic acid. If we use acids other than methanoic acid, then ketones can be prepared by passing vapors of acids other than methanoic acid at 573 Kelvin over manganese oxide. For example, acetic acid CH3COH plus another acetic acid CH3COOH. So COH of one and OH of other will combine to form H2CO3, which decomposes to H2O and CO2, and CH3 and COCH3 join together to form acetone. Similarly, when propanoic acid and acetic acid combine, butane 2-one is formed. Second method from carboxylic acids is aldehydes and ketones can also be prepared by distilling calcium salts of the acid. Calcium formate is distilled over, HCHO will be formed, and calcium carbonate. When calcium acetate and calcium formate combine, then these two will form calcium carbonate, and CH3CHO will combine to form acetaldehyde. Similarly, by distilling calcium acetate, acetone is formed. The calcium propanoate pente 2-one is formed. So 6 minus 1 carbon, 5 carbon ketone is formed. This method is not suitable for preparation of aldehydes except formaldehyde and also unsymmetrical ketones, because the number of products formed are greater, the yield is less, and also it's not pure. Cyclic ketones will be formed when dicarboxylic acid salts are dry distilled. For example, calcium succinate will form cyclopropanone, and calcium adipate when dry distilled will form cyclopentanone. From hydrocarbons, we can form aldehydes and ketones when terminal alkynes are hydrated, that is, water is added in presence of dilute sulfuric acid and mercury sulfate as catalyst. Water will get attached here. Addition is Markovnikov, so negative part OH comes here, H comes here, triple bond breaks to double bond. So CH3 COH double bond CH H will be formed, and then it undergoes tautomerism. The hydrogen moves here and the electrons come here to form RC double bond O and single bond CH3. So this is methyl ketone. So when terminal alkyne is hydrated with dilute sulfuric acid and mercuric sulfate. Ultimately, methyl ketones are formed. Acetylene will form acetaldehyde in the same reaction, and if non-terminal alkynes are used, then ketones will be formed. The limitation of the reaction is formaldehyde cannot be prepared by this method. And if we react alkynes with diborane and then oxidize with hydrogen peroxide in presence of alkali, in that case, during hydroboration, anti-Markovnikov addition will occur. Then that is, H will come to carbon containing less hydrogens, and BH2, remaining part, will go to carbon containing more hydrogens. So this triple bond is reduced to double bond. The one bond breaks, H is added here, BH2 is added here. When we carry out its oxidation using hydrogen peroxide in presence of alkali, then OH gets attached here. Then again tautomerism, and hydrogen will move here and these electrons will move here. So double bond oxygen is formed. So this is aldehyde is formed. Okay. So terminal alkynes will form aldehydes when reacted with diborane in presence of tetrahydrofuran and then oxidized using alkaline hydrogen peroxide. Non-terminal alkynes will give ketones. Again, one side H, another side BH2, and then OH gets attached, then tautomerism occurs and ketone is formed. So to avoid complication, because if unsymmetrical alkyne is there, then the ketonic group can be added to this position as well as this position. To avoid this, we use a bulky and sterically hindered borane, such as base 1,2-dimethyl propyl borane, which is also known as diisoamyl borane or diisoamyl borane. So using this, we can form ketones only at one position. Pure product will be formed. So interestingly, when we from alkynes, when we use dilute sulfuric acid and mercuric sulfate, methyl ketone was formed. But when we used diboranes and alkaline hydrogen peroxide, aldehydes are formed. Double bond containing compound. When we add ozone to it, both the bonds will be broken and ozone will be added in this manner. Then when we heat it with zinc dust and water, homolytic cleavage occurs. So one electron from this bond and one electron from this bond will form double bond here. Similarly, a double bond will be formed here. So we get two compounds with double bond oxygen. And ozonite on subsequent cleavage will form either aldehyde or ketone. For example, when we use ethene and add ozone to it, formaldehyde is formed. When we use symmetric alkene like but2-ene, then two molecules of acetaldehyde will be formed. On reacting with this compound, 2-methyl but2-ene, the bond will split from here, O will be added here, so one compound will be CH3CHO and other compound will be ketone, acetone. So you can see that the formation of products give you the indication of where the double bond is present. Next is by Wacker's process. So when we heat alkene with acidified palladium chloride aqueous solution in presence of cuprous chloride and air, then the bond breaks from here, oxygen is added, so product form will be acetone, CH3CO, CH3, and palladium chloride gets reduced to palladium and HCl is formed. This process is known as Wacker's process. If the two halogen atoms are attached to the same carbon, it's called geminal dihalide. From geminal dihalide, we can form an aldehyde or ketone by hydrolyzing it by reaction with aqueous KOH or barium hydroxide. Both the Cl will get replaced with OH, but this compound is unstable, so water gets eliminated from here and CH3CHO remains. So aldehyde is formed. Similarly, if it's a substituted dihalide, in that case a ketone will be formed after formation of dihydroxide, which is unstable, water is eliminated and acetone is formed. So that's all in this video. The remaining methods of preparation we'll take up in our next video. Thank you and have a nice day.